So just as a recap, we have looked at how if two functions are continuous, then the combinations of those functions, adding, subtracting, multiplying, dividing, multiplying by a constant, those are also continuous. We kind of builded from that idea to say all polynomials and rational functions are then continuous on their domains, to then build and say all of these types of functions are actually continuous on their domains. So again, as a reminder for you, whenever you are asked a question, like the example we had ended with yesterday, so if you're asked where is a function continuous, that is basically just asking you to find the domain of that function. So I am going to skip over example 3. I think I mentioned this yesterday. This is kind of just a combination of the two examples we did yesterday, but I want to go ahead to another type of, I guess, combining functions in a way, compositions of functions. So how we work with limits of composite functions. So here we have, and again, I called it theorem 8. That's what it's called in your book. So if f is continuous at some number b, b would still be an x value. And the limit as x approaches a of g of x is equal to b. So b is the limit of g. Then the limit as x approaches a of the composite function f of g of x is equal to f of b. So this is what that is saying, that if you have the limit of a composite function, so the limit as x approaches a of f of g of x, you are basically taking the limit as x approaches a of the inside function of g of x, and then whatever that limit is, you're evaluating f of that number. And then this is in words explaining that idea. So if x is close to a, g of x is close to the y value b for g of x, but then f is continuous at b, so b would be an x value for f. If g of x is close to b, then f of g of x is close to f of b. So that wording, whether or not that helps you, maybe it's confusing, this is the idea that you need to understand right here. That you can take the limit of the inside function and then just evaluate f of that limiting value. So here is an example of actually using that. We have to evaluate this limit as x approaches 1 of arcsine. Remember, arcsine is an alternative way to write inverse sine. So the limit as x approaches 1 of arcsine of the quantity 1 minus square root x over 1 minus x. And so as we're working through this, I noticed that I have a composite function. I have a function substituted into the inverse sine or arcsine function. So I could rewrite this as arcsine of the limit as x approaches 1 of 1 minus square root x over 1 minus x. I'm taking the limit of the inside, and then whatever I get, I'll evaluate what is arcsine of that. Okay, so the arcsine, I'm just going to keep rewriting that. I'm not doing anything with it yet. The question is, how do I evaluate this limit here? The limit of 1 minus square root x over 1 minus x. Or if I plug in 1, that should be the first thing. If I plug 1 in for x, I get 1 minus square root of 1, that's 0. And then 1 minus 1 on the bottom, that's also 0. Yes, I have to multiply by the conjugate. So 0 over 0, remember, is indeterminate. You can't say the limit doesn't exist when you get 0 over 0. You have to rewrite it. So I'd be multiplying this by the conjugate of the numerator. So I multiply by 1 plus the square root of x. And I multiply the denominator by the same thing. So that would all be inside that arcsine function. So I still have the limit as x approaches 1. So along the top, when you multiply by the conjugate, you are foiling. So I have 1 times 1 is 1. My two middle terms should cancel. 1 times positive root x, and then negative root x times 1. Those are going to cancel out. And then negative root x times positive root x would just be minus x. Be minus the square root of x squared, which is just x, so the square roots cancel out. And then on the bottom, always leave the denominator with a problem always leave that in factored form. Don't FOIL the denominator. You don't need to. So I still have the quantity 1 minus x times the quantity 1 plus square root x. And so that 1 minus x on the top is a quantity. I have the same quantity on the bottom. I can cancel that out. So I have arc sine of the limit as x approaches 1. I still have 1 on top. So that cancels out to just be 1. So I have 1 over 1 plus square root x. And now I can use direct substitution. I have 1 plus square root 1 on the bottom, which is 2. So I end up with arc sine of 1/2. What is the answer? No, so remember with this, so another way to write this is inverse sine of 1/2. So what you are solving when you evaluate this, you're figuring out sine of what is equal to 1/2. So your answer is an angle in radians. So sine of what angle is equal to 1/2? Pi over 6. All right, unit circle. You'll need to know. I think I've mentioned that. Maybe Mrs. Holba mentioned it because I did tell her to always tell her trig pre-calc students, if you ever ask why you're memorizing the unit circle, you need to know for calc. You guys learned the hand trick, right? So yeah, so it's 0, 30, 45, 60, 90, but in radians that's 0, pi over 6, pi over 4, pi over 3, pi over 2. And so if you want sine to be 1/2, because when you hold down your whatever angle, it's always like this number over 2. So if you want sine to be 1 over 2, you'd hold down this one, which would be pi over 6. And then cosine of that would be it'd be the square root of 1 over 2, so just 1 over 2. We will review that. I'll review that hand trick with you when we get into more trig. It does occasionally pop up, so it's not like a direct focus, but it happens often enough that you do need to be familiar with that. Yeah. Well, this is like, so arc sine of 1/2 or inverse sine of 1/2, the answer to that is the angle where sine is 1/2. So the answer to this is an angle. So it'd be 30 degrees, but because we always work in radians, it's pi over 6. All right, so any other questions, even just on that idea of you're taking the limit of your inside function and then evaluating the outside function. So with limits, you are allowed to do that with continuity. And that is as long as the limiting value you get on the inside, that number is in the domain of your outer function. So if you weren't able to evaluate, then we wouldn't be able to work with the limit that way. All right, why don't you actually do example 5? Work through example 5. And then we'll see if we get the same answer.
Where's pi?
It's under
Sine of pi.
You got any calculator.
So 0 plus 0 is 0. Yes.
Oh. Second is
Yeah, the second, if you have the 84, 83 seconds, here is your pi.
I might as well.
What's pi to do, Kyle? How do we express pi? The first thing we get is the square.
Alright, the limit is pi.
not done yet. You saw the pi again, which is 0.
The answer is 0. Pi. What is that? I don't think the limit is it's just 0. Plug in the 0. Plug in sine and you get
That's the answer.
So look at this. So it's sine of 5 plus sine of pi on the inside, which then this equals sine of pi plus 0. So sine of pi equals 0. So the answer is
Better. Yo, the Brewers season is just like ours. They get a win tonight and they're done. Wow. Well, same with mine. We made it to sections. We made it to sections.
so they are
First round. If you win 2 games, I think you play 5 games.
It should be 0. I know a lot of you are saying 0. It is 0. Look at how you would have it set up now. Again, sine of pi. I know a lot of you were typing that in your calculator. When you're allowed a calculator, that's fine. If you are not allowed a calculator, though, like this probably would not be a calculator question because you are expected to know what sine of pi is. So again, we'll be reviewing that that unit circle just so you know your exact values. That's another thing too is they'll leave them in exact. So if you were to have sine of an angle is square root of 3 over 2, that's how you have to give that answer. All right. The last theorem then still deals with composite functions, but it says if g is continuous at a and f is continuous at g of a, then the composite function f of g, given in either of these forms, they mean the same thing, is also continuous at a. So if your inner function is continuous at a, and then your outer function is continuous at g of a, so that y value, then the composite function is also continuous at a. And this in words says basically a continuous function of a continuous function is a continuous function. So in example 6, it's saying where are the following functions continuous? This again is basically asking you to find the domains of the composite functions. Okay, so that's a way to think of this is you're finding the domains for these questions. And so this one, if you did look at the practice from last night and you looked at 21 and weren't sure, going through part A here may help you remember how to work through those. So when you look at like in example A, look at this function. So my inside function, I'm just going to pull out the inside function here. 1 plus cosine of x. I would first find the domain of the function that's inside. So really you're looking at cosine of x. Wherever cosine of x plus 1, it's going to be continuous, or the domain would be wherever cosine of x that domain is. What's the domain of cosine?
All real numbers.
All real numbers. So cosine of x plus 1 still has a domain of all real numbers.
All real numbers.
So this domain is negative to positive infinity. So first look at your inside function. Are there any restrictions on the inside? In this case, there are not. Then I am taking natural log of 1 plus cosine of x. What is if I just had natural log of x, what is that domain? 0 to infinity. All right, so that means whatever you substitute into a logarithmic function, not just natural log, but any logarithmic function, whatever is substituted inside must be greater than 0. So to find the domain of this entire thing, I would have to set 1 plus cosine of x greater than 0 and figure out what x values meet that requirement. So there's no restrictions on 1 plus cosine of x. There is a restriction for the natural log that 1 plus cosine of x must be positive. So I would say here then if I subtract 1, cosine of x must be greater than negative 1. So from here, and I picked this problem on purpose with trig involved in it. How I'm going to think about this. If this was cosine of x is equal to negative 1, where is cosine of x equal to negative 1? So not 0. Pi, and then again at, not at 2 pi, at 3 pi, at 5 pi, at 7 pi. So this is true when x is pi plus 2 pi n, where n is an integer. Okay, so everywhere from pi and then adding a full rotation, you would have cosine is equal to negative 1. So cosine has to be greater than negative 1. That means, because everywhere else, the range for cosine is negative 1 to 1. So everywhere else, cosine is greater than negative 1. So that means x just can't equal any of these values. They're excluded. So I'm not going to write this in interval notation because you have infinitely many values that happens at. So this is how I would write it. I would use the set builder for this. I would say all x such that x cannot equal pi plus 2 pi n, where n is an integer. Okay, so that one's a little trickier just because of the trig involved with the inequality that's involved with the natural log. That's why I picked that example to go through. They're not all like that. But any questions on that? Does that make sense? All right, so if we look at part B, this one's more straightforward. We have sine of x squared. So you first look at just x squared. What's the domain for x squared? All real numbers. And then you have sine of x squared. So if we just had sine of x, that domain is also all real numbers, so there's no restriction. So the domain, or where this is continuous, is everywhere negative to positive infinity. So look at the inside function. Are there restrictions? Outside function, are there restrictions? If there are restrictions on the outside function, you have to apply those to the inside. Okay? But again, it's a domain question. It's asking you for the domain. Yes, Kyle. If they're on the inside, Yes, so then say you had restrictions on the inside and no restrictions on the outside, your domain, your overall domain would be whatever the restrictions are on the inside. And then if there were also restrictions on the outside, you'd be finding the intersection of the domains. All right, so looking at these problems, these would be your practice if you hadn't looked at those yet. I am going to pass out, because we have plenty of time to talk about the intermediate value theorems. That's all this next thing is one theorem. It's an important theorem. I'm not downplaying it at all. You do need to know this theorem.
You need to know the other ones by like number.
You don't need to know the other ones by number. You just have to know how to work with those types of problems. But this theorem you need to know. Okay, there are 3 value theorems in calculus. The intermediate value theorem is the first one that we covered. So there are 3 of these value theorems. And note, if you see IVT or you refer to IVT, that is common, like just a common shorthand way to refer to intermediate value theorems. So if you say IVT in reasoning, that's okay, that's allowed. On an AP test, whoever's grading it will know what you're talking about. So intermediate value theorem, there's also the extreme value theorem and the mean value theorem, and those are both in chapter 4. So this does come up, and whenever you're using this, you do have to refer to it exactly. So you do need to know this theorem. This is basically proving that a value exists. What's weird about it is it doesn't matter what the value actually is. So it's not asking you to find a value. It's asking you to determine if one exists. So these are all just theorems that are looking to see do values exist, but not actually have you find them. That would be a separate question. So this is an important property of continuity because in order for the intermediate value theorem to be applied, the function has to be continuous. So here's the idea. If you're given a function on an interval, that function will hit every y value between the starting and ending y values as long as the function is continuous. So if you think of a continuous function on an interval, you have a starting point and an ending point, and as long as it's continuous, there's going to be no holes or asymptotes or anything. It's going to hit every y value on that interval. That's the idea. So here's the actual theorem. It says suppose f is continuous on the closed interval from a to b. So this would be an x range. And then it says let n is a y value. So let n be any number between f of a and f of b. So f of a would be like your starting y value, f of b would be your ending y value on that interval. And then here's the conclusion. Then there exists a number c, so c is an x value. There exists a number c in the open interval from a to b, meaning c can't be one of the endpoints. It has to be in between a and b, such that f of c is equal to n. So I know the wording might be confusing, but try to understand this idea because of continuity. Hopefully that makes sense. So here's 2 pictures of this. So you have a graph of your function. Here's a to b. So here's f of a. Here's f of b. And then notice it's letting n is some y value between f of a and f of b. And as long as the function f is continuous on that interval, then at some x value c, f of c will equal that y value n. And it might hit it once. The next picture shows the same exact graph, but it shows different c values. So it might hit it a few times, depending on what the value of n is. Again, the theorem doesn't care how many times or how many c values equal n, or f of c equals n. It doesn't matter. The theorem just wants you to say that it exists. So that's what's weird about it. here's how you apply it then. So if we look at example 1, a lot of the time these are used, or the IVT is used to show roots of an equation or where y value is 0, but that doesn't always have to be the case. So it says use the IVT to show that there is a root, which would be a 0, of this equation between 1 and 2. So 1 and 2, those would be your A and your B values. Here's what you need to show. Anytime you are using IVT as a conclusion, you must state before you use the IVT that you know the function is continuous. Because the theorem only works if the function is continuous on that closed interval. So if I'm looking at this, I'm trying to show that this equation is true. So if I think of this as my function f of x, I'm trying to show that somewhere on the interval from 1 to 2, that the y value is equal to 0. So this would be the n that they're referring to in the theorem. So here's how I'm going to start. I'm going to say f of x, which equals 4x cubed minus 6x squared plus 3x minus 2. What type of function is this? Well, I heard a few things, but polynomial, the most general. Polynomial, where polynomial is continuous? Everywhere. So f of x is continuous on negative to positive infinity, and therefore on the closed interval from a to b, which is 1 to 2. So you first want to state that the function you're working with is continuous on your closed interval. In this case, since you don't have to state f of x is a polynomial, but I just stated where it's continuous, so therefore it is continuous from 1 to 2. Then I'm going to do some work before I make my conclusion. So what I'm going to do is I'm going to find what is f of 1 and what is f of 2. So you want to find the function values or the y values of your endpoints. Because what you're trying to show is that 0 is in between those two y values. So f of 1, anybody have what that is? Negative 1. And then f of 2 is 12. All right. 0 is in between negative 1 and 12, right? So I'm just going to make a note here. So I would have f of 1 is less than 0, which is less than f of 2. So I just showed that my n value is in between f of 1 and 2. That's what you want to see happen. So I'm going to say here, since this, I'm just going to show this again. So since f of 1 is less than 0, which is less than f of 2, or rather, since 0 is between f of 1 and f of 2, then by the IVT, there exists a number c in the open interval from 1 to 2 such that f of c is equal to 0. Okay, so I know you do need to, you don't have to say exactly word for word what I just stated. You have to know enough about the theorem and the conclusion, meaning you need to practice using it so you understand what it's looking for to make your conclusion. And then if I go back to the question, this would probably be enough. But I'm also going to say, because this said to show there's a root, I'm just going to end with, thus there's a root of the equation 4x cubed minus 6x squared plus 3x minus 2 equals 0. Okay, I'm not saying what c is. That's not what this question wants you to find. It just wants you to show that it exists. Okay, so you need to, again, first state that your function is continuous on the closed interval. Find your two y values to show the y value you're concerned with is in between them. And then you make your conclusion. By the IDT, there's a number c in the open interval such that f of c equals that y value. All right, any questions on that one? I would like you to then answer or do the same, or do example 2. But for this one, it says show that the equation cube root of x equals 1 minus x has a root. So what you're going to have to do first, anytime you're looking for a root, you are looking for the y value to be 0. First, make this equation, make one side equal to 0. Okay, the other one was already set up that way. Get one side, it doesn't matter which side, but get one side of this equation to equal 0 before you start. Okay, so just try writing this one out, and then you can compare it to what I have. I'll give you a moment. If you have questions, let me know.